The TRAPPIST-1 system is not humanity's best hope for finding alien life. It is something more important than that. It is the first system where we can actually test, planet by planet, whether rocky worlds can hold onto an atmosphere around the most common type of star in the universe. 7 Earth-sized planets orbit a single star, 40.66 light-years from here, in the constellation Aquarius. Every single orbit would fit inside the distance between our Sun and Mercury. The star they circle measures roughly 12% the radius of the Sun, barely larger than Jupiter. Not a failed star, a real one, fusing hydrogen, producing light, driving weather on worlds we can now observe directly. The central question is not whether life exists there. What we need to know is simpler and far more consequential. In a system this compressed, this old, this violent, what can a rocky world hold on to? TRAPPIST-1 carries the catalog designation 2MASS J2306 292 500 and 2285. Classified as an ultracool red dwarf, it possesses only about 9% the mass of our Sun and a surface temperature of approximately 2566 Kelvin. Cool enough that, if you could stand at the distance of Earth's orbit, the star would appear a deep, dim crimson, barely visible against the black. This faintness is deceptive. The system is 7.6 billion years old, 3 billion years older than our solar system. Stars this small burn their fuel with extraordinary efficiency. Our Sun will exhaust its hydrogen in roughly 5 billion years. TRAPPIST-1 can remain stable for up to 12 trillion years. Let that settle. 12 trillion. The current age of the entire universe is 13.8 billion. TRAPPIST-1 has barely begun. Longevity comes at a cost. Kepler's K2 mission recorded 42 flares from TRAPPIST-1 in just 80 days of observation. Some were large, complex, multi-peaked events, the kind capable of altering a nearby planet's atmosphere irreversibly. The star's magnetic field measures approximately 600 Gauss in mean intensity. By comparison, the Sun's average surface field is about 1 Gauss. That magnetic field drives intense chromospheric activity. It may also trap coronal mass ejections before they reach the outer planets, a potentially protective effect. Or it may funnel charged particles directly into the orbital plane, where all 7 worlds reside. The data does not yet distinguish between these outcomes. What is known, the star is small enough, Jupiter-sized, that when its planets transit across its face, they block a measurable fraction of its light. This is what makes the system uniquely valuable, not its habitability, its observability. JWST turned its instruments toward TRAPPIST 1b in 2023. The innermost planet, tidally locked, one hemisphere permanently facing the star, the other locked in eternal night. The dayside temperature, approximately 500 Kelvin. What JWST measured was thermal emission, heat radiating from the planet's surface. If an atmosphere existed, it would redistribute that heat. Winds would carry warmth from the day side to the night side. The temperature difference between the 2 hemispheres would narrow. It did not narrow. The heat signature matched bare rock. No circulation, no insulation, no atmosphere. This is not speculation. This is measurement. TRAPPIST 1c, the second planet outward, told a similar story. JWST observations found no thick CO2 envelope, no Venus-like greenhouse. The planet receives 2.27 times Earth's solar flux, enough to bake the surface to roughly 342 Kelvin, if nothing but stone absorbs the light. 2 planets measured, 2 atmospheres absent, a pattern forming. Then the boundary shifts. The next world outward is TRAPPIST 1d, sitting at the inner edge of the habitable zone, receiving 1.15 times Earth's flux. Models suggest tidal heating, gravitational flexing from its resonant orbit, could drive volcanism beneath the surface, pumping gas back into any atmosphere the star tries to strip away. If tidal heating is active on TRAPPIST 1d, it should be producing gas. Volcanic outgassing should be measurable. An atmosphere, even a thin one, should leave a trace. JWST has not yet confirmed one. If you have a thought on where this pattern leads, Whether the outer worlds break it or confirm it, leave it below. The question sharpens. If the engine is running, where is the exhaust? The engine is running. The question is where the exhaust has gone. TRAPPIST 1D orbits at 0.02144 AU from its star, roughly 3.2 million kilometers. Mercury, the closest planet to our Sun, never ventures closer than 46 million kilometers at perihelion. TRAPPIST 1D sits more than 14 times nearer to its star than Mercury does to ours. At this proximity, tidal forces do not suggest themselves gently. They lock, they flex, they reshape. What separates this planet from the two scorched worlds inward is arithmetic. TRAPPIST 1D receives approximately 1.15 times Earth's solar flux, enough energy to sustain liquid water on a surface, provided an atmosphere exists to regulate temperature and pressure. Strip away that atmosphere, and the planet becomes another bare rock. One hemisphere baking, the other freezing. The conditions required for survival are specific. Sufficient atmospheric pressure to prevent water from boiling into vacuum, enough greenhouse warming to distribute heat across the surface, a radiation shield, either magnetic or atmospheric, capable of deflecting the charged particles accelerated by the star's frequent flares. JWST has not yet confirmed that any of these conditions are met. The absence is not conclusive. Thin atmospheres, those with surface pressures well below Earth's, fall beneath the current detection threshold of JWST's mid-infrared instrument. A world could possess a tenuous envelope of carbon dioxide or nitrogen, enough to drive rudimentary weather patterns, and the signal would vanish into the noise of the star's own infrared output. But the pattern established by planets B and C presses against every model. 2 inner worlds measured, 2 thick atmospheres absent. Stripping, it appears, is efficient this close to TRAPPIST-1, which brings us to the mechanism responsible. TRAPPIST-1 is 7.6 billion years old. Our entire solar system, Sun, Earth, Jupiter, everything formed 4.6 billion years ago. By the time our planet's first single-celled organisms were experimenting with photosynthesis, TRAPPIST-1 had already been burning for 3 billion years. It has been flaring for all of them. Kepler's K2 mission observed TRAPPIST-1 continuously for 80 days. During that window, the spacecraft recorded 42 distinct flare events, one every 1.9 days. Some were brief, sharp spikes of ultraviolet and X-ray energy lasting minutes. Others were complex, multi-peaked eruptions that sustained elevated radiation output for hours. Each event accelerated charged particles, protons and electrons outward from the star's surface at velocities approaching a significant fraction of the speed of light. When those particles reach a planet without a magnetic field, they interact directly with the upper atmosphere, molecule by molecule, atom by atom. The gas is ionized and swept into space by the stellar wind. On Earth, this process is largely deflected by our magnetosphere, a bubble of magnetic force generated by the churning liquid iron in our planet's core. That dynamo requires rotation. Specifically, it requires differential rotation between layers of conducting fluid. TRAPPIST 1D is almost certainly tidally locked, one face permanently toward the star, one face permanently away. A tidally locked rocky planet rotates once per orbit, in this case, once every 4.05 Earth days. Whether such slow rotation can sustain a magnetic dynamo remains an open question in planetary science. Some models suggest it can, if the core is large enough and convection vigorous enough. Others predict the dynamo dies within the first billion years. 7.5 billion years have passed since this system formed. If the dynamo failed early, the atmosphere has been unshielded for longer than Earth has existed. Consider then what protects from the other direction. TRAPPIST-1's magnetic field measures approximately 600 Gauss in mean intensity. The Sun's average surface field is roughly 1 to 2 Gauss, though sunspot regions can reach several thousand. A field of 600 Gauss across the stellar surface is extraordinarily strong for such a small, cool star. It carries an unexpected implication. Coronal mass ejections, the massive plasma clouds that accompany the most violent solar flares, must travel outward through the star's own magnetosphere before reaching interplanetary space. A magnetic field this intense may be capable of trapping those ejections, containing the plasma in magnetic loops before it can escape. This is not confirmed through direct observation. It is a hypothesis derived from magnetohydrodynamic models of ultracool dwarf activity, but if correct, the implication reshapes the habitability calculation entirely. The same star whose flares threaten planetary atmospheres may also possess a magnetic cage that prevents the worst of those flares from reaching the planets at all. The violence may be self-limiting. The question is where the boundary sits, how far from the stellar surface the magnetic containment holds, and at what distance the stellar wind breaks free. Planets B and C orbit inside that boundary. The data confirms it. Their atmospheres are gone, or were never substantial. TRAPPIST 1D sits at the edge. The data does not yet confirm which side. Beyond it lies TRAPPIST 1E, the fourth planet, orbiting at 0.02928 AU. It receives 0.66 times Earth's solar flux, less energy than our planet gets from the Sunday. If it were bare rock, its equilibrium temperature would settle around 246 Kelvin, roughly minus 27 degrees Celsius. Cold, but not frozen beyond recovery. A modest greenhouse atmosphere, even one a fraction of Earth's thickness, could raise surface temperatures above the freezing point of water. JWST has not yet observed TRAPPIST 1E with the precision applied to planets B and C. No thermal emission measurements, no transit spectroscopy capable of resolving atmospheric composition. The planet exists, for now, in a space defined entirely by what has not been ruled out. That silence carries its own weight. For the first time in this system, the data does not say no. What the data hints at next introduces a variable that complicates every model built so far. TRAPPIST 1E is not orbiting in isolation. It is locked in a resonant chain with its neighbors, a gravitational dance where each orbit is an integer ratio of the next. With planet D, that ratio is 3:2. Every 2 orbits of TRAPPIST 1E, planet D completes exactly 3. The gravitational tug at each conjunction flexes the planet's interior, generating heat through friction in the mantle and core. On Earth, tidal heating is negligible. The moon's influence is too weak. On Io, locked in resonance with Europa and Ganymede around Jupiter, tidal heating drives over 400 active volcanoes and resurfaces the entire moon every million years. On TRAPPIST 1E, the effect falls somewhere between these extremes. If tidal heating is active, it could sustain volcanic outgassing, carbon dioxide, sulfur dioxide, water vapor, replenishing an atmosphere faster than the stellar wind strips it. The absence of a detected atmosphere may not mean the planet is dead. It may mean the atmosphere is thin, transient, cycling between eruption and erosion on timescales we have not yet observed. The habitable zone is a mathematical boundary, not a promise. TRAPPIST 1E orbits within it, 0.02928 AU from its star, receiving 0.66 times the solar flux that reaches Earth. Liquid water could persist on its surface. That single word, could, carries the weight of every unknown variable in planetary science. An atmosphere thick enough to trap heat, a magnetic field robust enough to deflect charged particles, a geological interior active enough to replenish what 7.5 billion years of stellar bombardment has eroded. Remove any one condition, and the habitable zone becomes a label on a frozen rock. The data forces a choice that contradicts expectation. Around our Sun, the habitable zone stretches from roughly 0.95 AU to 1.37 AU, a band tens of millions of kilometers wide. Around TRAPPIST-1, that band compresses to a sliver between approximately 0.022 and 0.032 AU. The entire habitable zone of this system fits within a region smaller than 1/10 of Mercury's orbital distance from the Sunday. Place TRAPPIST 1E in our solar system at its current orbital radius, and its surface would be molten glass. Yet here, at 0.02928 AU from an ultracooled dwarf radiating at 2566 Kelvin, the energy budget balances differently. The star emits most of its radiation in the infrared, wavelengths longer than visible light, carrying heat rather than the photochemical energy that drives Earth's biosphere. This spectral shift changes everything. A hypothetical atmosphere on TRAPPIST 1e would not interact with starlight the way Earth's atmosphere does. Carbon dioxide, water vapor, methane, each absorbs infrared radiation at specific wavelengths. An atmosphere tuned to retain infrared heat could warm the surface efficiently. One tuned wrong triggers a runaway greenhouse, boiling away whatever liquid water the habitable zone promised. The margin between frozen wasteland and runaway furnace is narrow. Models suggest it may be as thin as a few hundred millibars of atmospheric pressure. A new variable enters the equation, one that does not apply to any planet in our solar system at this orbital distance. TRAPPIST 1e is tidally locked. One hemisphere faces the star permanently, the other faces the void. On the day side, temperatures could reach 280 Kelvin with a modest atmosphere just above the freezing point of water. On the night side, without atmospheric heat transport, temperatures plunge below 150 Kelvin. The difference between these hemispheres is not a gradient, it is a wall. Habitability depends entirely on whether wind exists. Circulation carries heat from the day side to the night side, moderating extremes, preventing the dark hemisphere from becoming a cold trap that freezes out atmospheric gases permanently. Without it, carbon dioxide condenses in shadow, atmospheric pressure drops. The remaining gases on the day side escape more easily into space. The planet cannibalizes its own atmosphere through geometry alone. Even a thin envelope, perhaps 0.1 bar of CO2, could sustain a circulation pattern strong enough to prevent this collapse. General circulation models for tidally locked planets predict a single massive convection cell, air rising on the day side, flowing to the night side at altitude, cooling, sinking, and returning along the surface. The pattern is alien to anything on Earth, yet physically inevitable given the heating asymmetry. JWST has observed TRAPPIST 1e during transit. The telescope measures starlight filtering through the planet's limb, the razor-thin edge of its silhouette, searching for absorption signatures that betray atmospheric composition. No confirmed detection has been published. The signal-to-noise ratio demands multiple transits, each adding fractional clarity to a measurement operating at the instrument's limits. This absence is not silence, it is constraint. A thick atmosphere, anything resembling Venus's 90-bar envelope or even Earth's 1-bar nitrogen blanket would have been detected. Its absence means that if TRAPPIST 1e possesses an atmosphere at all, it is tenuous, possibly cycling between volcanic replenishment and stellar erosion on timescales shorter than our observation window. The implication reframes the entire search. Roughly 75% of all stars in the Milky Way are red dwarfs. If rocky planets orbiting them cannot retain atmospheres even within the habitable zone, the number of worlds capable of supporting liquid water drops by orders of magnitude, from billions to perhaps thousands. TRAPPIST 1e is the fulcrum on which that estimate balances. Let that settle. TRAPPIST-1 formed 7.6 billion years ago. Life on Earth required approximately 3.5 billion years to progress from chemistry to single-celled organisms. If any world in this system achieved even minimal habitability, it has had more than twice that duration. The next JWST observation window opens in 2026. The data from that pass will either confirm the pattern of stripped atmospheres across every measured world in the system, or it will break it. The data gives a direct reply. TRAPPIST 1b retains no atmosphere. Thermal emission measurements confirm bare rock baking at approximately 500 K with no heat redistribution. TRAPPIST 1c shows no thick CO, 2 envelope, no Venus-like greenhouse, nothing above JWST's detection threshold. TRAPPIST 1d, despite sitting at the habitable zone's inner edge with plausible tidal heating, has yielded no confirmed atmospheric signature. 3 planets measured, 3 null results. The innermost worlds of the TRAPPIST-1 system have been stripped. However, this pattern carries a boundary. Planets E, F, and G orbit at 0.02928, 0.03853, and 0.04687 AU, respectively. Each sits progressively farther from the star. Each receives progressively less radiation. Each experiences progressively weaker stellar wind pressure. If atmospheric survival follows a distance gradient, and the inner planet data suggests it does, then the outer worlds represent the zone where retention becomes physically possible. Tidal heating from the resonant chain could sustain volcanic outgassing on planet E. Planets F and G, colder and farther out, may harbor ice-covered surfaces with subsurface reservoirs warmed from within. None of this is confirmed. All of it is testable. TRAPPIST-1's importance extends beyond its own 7 worlds. What the data has provided so far is not a habitable world. It is something more structurally consequential, a calibrated baseline. We now know the stellar flux at which atmospheric stripping overwhelms retention for planets orbiting a 7.6 billion year old ultracooled dwarf with a 600 Gauss magnetic field. We know that tidal locking alone does not guarantee atmospheric loss. The mechanism depends on distance, magnetic shielding, and replenishment rate. Each null detection from the inner planets narrows the parameter space for the outer ones. Each future observation of planets E, F, or G will either confirm that the stripping gradient extends across the habitable zone or reveal the threshold where geology and distance combine to preserve a gaseous envelope. Repeated transits will stack signal, pushing sensitivity below current thresholds, searching for the faint spectral fingerprints of carbon dioxide, water vapor, or molecular nitrogen. If a thin atmosphere is detected, the model of red dwarf habitability shifts from improbable to conditional. If no atmosphere is found, the inner boundary of atmospheric survival around ultracooled dwarfs moves outward again. Attention turns to F and G, the colder, more distant siblings where ice may matter more than air. The system is not humanity's best candidate for finding life. It is the first laboratory where we can determine whether life around the most common stars in the universe is even permitted by physics. That distinction matters. Discovery is a single event. Calibration is a framework that applies to every red dwarf system measured afterward, and there are roughly 250 billion of them in this galaxy alone. TRAPPIST-1 will outlive our Sun by a factor of 2,000. Long after every solar-type star in the Milky Way has swollen into a red giant, shed its outer layers, and faded into a white dwarf, this dim ember in Aquarius will still be fusing hydrogen. 12 trillion years of stability lie ahead. The current age of the universe, 13.8 billion years, amounts to barely 0.1% of the star's total lifespan. What has been measured across the preceding analysis is not a snapshot. It is a system already 7.6 billion years into its evolution, 3 billion years older than Earth. The initial chaos of formation has long since resolved into gravitational equilibrium. If atmospheres were stripped, that stripping began billions of years ago. If atmospheres survived, they have persisted longer than any complex organism has existed on our planet. 12 trillion years of stellar stability remain. The question is not whether we are looking in the right place, but whether we arrived early enough to recognize what endurance looks like.